Welcome to this presentation, still under the CGS series and on the angle trisection solutions. In this video, we're going to look at the trisection of an angle within the third degrees configuration using the Alex's method. I will perform the constructions using, as usual, the GeoGebra software. And here it is. We're in the drawing pad of the geometry environment. I'm going to create an arbitrary angle that is less than 30 degrees. Of course, I must have the 30 degrees configuration for me to be sure the angle is less than 30 degrees in magnitude. And I'll have my 2 points. I just pick any that way. And the third point, I'll just place it after I have constructed 30 degrees, anywhere within the 30 degrees configuration. So that's exactly what I'm going to do. I erase the nested tools for use in the construction. With the canvas tool, I can easily create 30 that way. Sorry, I need to sharp that clearly. And using the labeling tool here, I mark my 60. Next, I'm going to do the bisection of this. Using the angle bisector tool to give me my 30 degrees configuration. That's the environment I'm interested in working at. So I label this as 30 degrees. As usual, again, I change this for security purposes. I'm using the word security just to create some impression that we should be within that configuration. And I give it that color. Now I'll use the labeling tool to mark another point within this configuration, either outside or within the scale here. So I can just place on the curve just a point in that way. I want to be sure it's on the curve. I can just place it again anywhere. Okay, that's fine. I can proceed with that. I'm going to use the line segment, not complete line this time around. Join it, and again join here. I want to trisect this. Then give it a different color for distinction purposes and good appearance too. Now I impose the other condition that I need to have a midpoint of the line AB that way. I do some geometric transformations to create 2 more points for use or for later use in the feature of this video. And those are the points F prime and B prime. These are simple techniques. I'm not teaching the use of GeoGebra here, but just demonstrating the constructions. Okay, with that, I'm going to use the straight line tool to help me join this point E through to point F prime. And since I would like to construct other lines parallel to this, I give it a different characteristic color. And using the compass tool now, we perform the Alex method of trisecting this line. It's just that simple. Fine, I'm interested in this line. Before that, I need to have a tool, that tool to label this. I'm interested in that point of intersection. So I'll carry that compass tool, pick that the segment subtending the angle CF prime A, and place it here. I repeat the same procedure again, carry that, place it here. I can give these 2 circles just for distinctive purposes a different color close to that, and this one too a different color. Okay, same color because they hold the same property or characteristics. I will need to use another tool here to zoom in the figure so that I can accurately label the point of intersection between this second curve and the curve I've just placed here. Here is the point I'm talking about. This. Next, I zoom out to go back to my drawing pad on the GeoGebra. So that is it. To draw the parallel lines, I'll consider the points A and F. So I draw a straight line through points A and I, and another one through points F and H. That mark this as that, and I mark another one here at that. I'm interested in the points of intersection between this, our line, our master here, our friend here, and the blue lines. Those are the points of intersection, form the trisection points. For the line, of course, not the curve. And our friend has that. Pick another one here. I also label this as the other point. And I'll zoom out the figure to go back to the drawing pad that way. Now the next step, I'll draw straight lines to mark all sections the curve BE, and the first point I will start from point F prime through K and through point A, and the last point, the other point is D, not H. I have to be very careful. One has to be very keen on how you place these points on the GGBRA, especially when the figure is this congested. So I need this point of intersection between the black lines and the black curve. That's the one of the points. Zoom out, get to the other one. This is the point. Okay, I have got what I needed. I need the curve ML. I'll use the compass tool to carry the code LM or ML, and using the point B prime make an arc that cuts the curve at a point. I will just mark this as point. Sorry, I'll change the appearance of that into this. Fine. And mark or label this point of intersection between the outside curve and that as point N. I would like to measure the size of anchor E, A, and B, the 3 points, in the scale of 0 to 180. It is 22.68. So what should be the size of this anchor I hope to have trisected, or which hopes to have trisected the anchor 22.68? It's 7.56, and it looks correct. Let's confirm from the scientific calculator. If I take 22.68 divided by 3, I get 7.56 exactly. So that's how we can perform the trisection of anchors within the configuration 0 to 30. Some other times you might find an angle is very close to 30. You might decide to reduce it. Of course, its bisection will be within the configuration, and you get these accurate results. So that is it with Alex's method. How simple it appears. It's just the way it reads from the document. We can stretch this to see if there were some more variations. That's 4. There's a 7 here, it will add, and it looks correct. It really looks correct. It's interesting construction. Any measurement is not part of the proof, but it's quite an interesting technique. We go back to the slides. Sorry. And that makes the end of this presentation. Thank you for viewing the video. Please remember to subscribe and like this channel to be updated anytime I upload new videos of this kind. In the next presentation, we'll now perform the procedure in a known angle. For example, I'm going to trisect an angle of 45 degrees. I hope to have responded into many questions up to that point. Now I'm going to the real life applications of the known angles. Within the we have demonstrated in the first video how the method works within the 3rd degrees configuration. I have gone in the next video to an angle over the 3rd degrees configuration. This one we have worked to an angle within the 3rd degrees configuration. And one observation we have seen, all one would make from the 3 videos, is that as the size of the encode reduces, the method shows better results in terms of accuracy as you go from 0.1 to infinity. So in the next video, I'm going to show how to trisect an angle 45.